What if we take the smallest visual language model there is and ask it to control a robot just from the camera images? Will it even work? Will it get stuck in the boxes? Will it make the robot catch fire and explode? Is there life on Mars? In today's video, I'm trying to find answers to all of those questions. Well, maybe not the last one. To do that, I'm going to resurrect a decade-old humanoid robot, collect real-world data, do some fancy machine learning work, and see if the robots can survive in my office. Look at this. This is almost a museum artifact at this point. This is RAPIRO, or Raspberry Pi Robot, which was launched in a Kickstarter campaign in 2013 by Japanese engineer Shota Ishiwatari. It was a rather successful project that unfortunately did not have continuation. By the time I found it in Shenzhen office, it was already deeply end of life. Regardless, I love tinkering with a robot, so I fixed it and added some simple speech recognition capabilities to it.
Test. Stop.
And I forgot about it until my last visit to Shenzhen. That time I asked if C Studio can donate this unit to my YouTube channel.
For science.
Which they did. Now when I have the robots, I want to give it a task. Explore my office and avoid bumping into the things. It's a trivial task that can be solved in many ways. I could simply install a couple of distance sensors and write code with if-else conditions. It would probably work just as fine or maybe better, but I am building something different here. I'm going to pass the camera image from head-mounted camera, it's a simple RGB Raspberry Pi 2 camera module, to Hugging Face SmolVLM or visual language model, together with a text prompt, and then use the text output to control the robot direction by executing correct motion function. It's a toy problem really, kind of like Titanic dataset or cat-dog classifier, but for embodied AI. We imitate a much more complex setup of advanced robots, where multimodal AI processes video, text data, and robot sensor data to directly control actuators of the robot to complete the task. Doesn't matter what kind of machine learning we do, it starts with data. The data in this case will be images plus text prompts as inputs and robot direction as an output. I installed Raspberry Pi 02 in the robot head and connected it to robot control board via UART and also attached a MIPI CSI camera. Then I vape coded a simple UI for robot control, which allows me to see a real-time camera feed, execute the action, and then logs the action and the image into the dataset. Off we go! I did a few attempts at data collection. I started with 50 images and then added a couple of dozen more, while testing model on the dataset. First I was using the handwritten script to eyeball the accuracy, and then I switched to using weights and biases weave to log the results. Quickly I realized that off-the-shelf model does not perform well at all, getting accuracy about 30 to 40%. If you think about it, it makes total sense. The visual language model consists of the language model itself, a visual tower aka image encoder, an adapter between these two. So we got the image here, which turns into tokens, image tokens, and is being fed together with the text tokens into a language model. If the original image encoder was not trained to emphasize the information about the distance to the objects and then location of the objects related to the camera, then it doesn't matter the reasoning capabilities of the language model, it will not perform well on this obstacle avoidance task. So the right thing to try next would be fine-tuning both the image encoder and the language model on my dataset with LoRa. Not this LoRa. I mean low-rank adaptation, or the technique used for fine-tuning transformer models. It's done pretty easily with either official Hugging Face Jupyter notebook for fine-tuning or SmolVLM fine-tuning scripts. I chose the second option. The accuracy with default parameters rose to 69.5%, which was much better, but still barely acceptable. I consider 80% to be passable, according to the 80-20 rule. Garbage in, garbage out, so I went back to the data, vape coded a data viewer, and went through all the samples to make sure that they're correct. To my surprise, a lot of them were not. Since I was in the same room when collecting the data, oftentimes I would look at the robot and not on the screen, which means that I would see the obstacles that were not in the camera. After I relabeled the images so they would make more sense if you only have the access to the information from the camera, the accuracy increased a bit more. Finally, I increased lower rank and alpha parameters from default ones, so fine-tuned model could absorb more information. All in all, I got 90% accuracy on a training dataset. You really should not count on training accuracy, but in this case it was easier for me to test the robot in the field rather than separately collect validation data. So I added a big red button on robot interface and I am ready to press it. For now, the language model actually runs on a PC with a consumer-grade GPU. It's connected to Raspberry Pi over local network. But as I showed in earlier videos, it's definitely possible to run SmolVLM on Raspberry Pi 5. The only reason I'm not doing that is the power issues I encountered. I'm going to fix that and add a couple of more features in future videos. Like this video and subscribe to the channel to see that.